Hey everyone, in this video we're going to talk about anti-differentiation by parts. And this is a method that can be a bit frustrating at times as it takes some practice and it doesn't necessarily always work out for the best. For example, sometimes when we do anti-differentiation by parts, it's very easy to choose the wrong thing or the wrong part of the equation to make u or dv equal. And sometimes it comes out where after we've sort of applied the parts formula that it's more complicated than we originally thought or we originally had. So it's one of those methods that's going to take a little bit of practice. It's going to take some getting used to the fact of what to choose for substitution or what part to make equal to u or what part to make equal to dv. So I'll try to highlight those things as we kind of go through some examples here. But anti-differentiation by parts really is a way to sort of undo the product rule. So that's what we have right here, is we see that if we take the derivative with respect to x of u times v, that's going to be u times the derivative of v plus v times the derivative of u. Well, if we want to go backwards, that means that the integral with respect to x of each term should give us a path back to where we started. Okay? So in this case here, on the left side, right, if we take the derivative and then the antiderivative, we should get right back to where we started. So that's just going to come out to be uv. And then over here, we get our dx's to cancel in both cases. So this is going to equal the integral of u dv plus the integral of v du. Okay, and if we just do a little bit of rearranging, we're going to move this, or I should keep that where it is and just move this to the other side. We can say then that the integral of u with respect to v is equal to u times v minus the integral of v with respect to u. Okay, and again, that's just a matter of flipping sides and then subtracting this right over here. But this nice complicated thing right here, this is our differentiation by parts formula. So that's the piece that we're going to have to make sure that we sort of know and understand and are able to use. So let's see how we would go about using that in terms of finding an antiderivative. So let's say we had this example here. We'll say we want to find the integral of x cosine x dx. Okay, and in this case here, I'm going to make sure that I pick the proper term for u and the proper term for dv. Now, when picking something for u, I always want u to be something that's very easily differentiated. In other words, u wants to have a very simple derivative. So if I make u equal to x, I know that the derivative of u is very, very simple. du is simply going to equal 1 dx. Okay? Well, that means that if u is equal to x, then the dv part must be equal to cosine x dx. All right? And whatever I make dv, I want that to be a simple antiderivative, or in other words, it's very simple to take the integral of that. All right? So that means then that v would be the antiderivative of dv, so the antiderivative of cosine x would be the sine x. Okay, so now I've got all of my parts here. I can go ahead and start plugging into this formula right here. So I know that my integral here is going to equal u times v, so that's going to be x times sine x minus the integral of v du. Well, v was sine x. Right, v was sine x. And then the du was equal to dx, so I'll put that in here. And now the nice part about this is the integral that we see right here is very, very simple to take. We already know what the antiderivative of sine x is, so we can just go ahead and say that, all right, this is going to come out to be x sine x minus the negative cosine x plus c, right? Our constant of integration right there. So, go ahead and just fix our sign right there. So we're going to get x sine x plus cosine x plus c. And that would be equal to our integral that we had right up top here. Okay, let's try one more example and see where it can get a little bit more challenging. Okay, and so let's say we had this example here. We have x squared e to the x dx, and again, we're going to use our anti-differentiation by parts formula over here. So the first thing we want to do is we want to pick something for u, and we want to pick something for dv. U has to be something that's easily differentiated. So x squared is easily differentiated, so is e to the x. But remember, I want dv to also be very simple to take the antiderivative. So if I look at each of these, the one that is easily, we easily take the antiderivative of would definitely be e to the x. And that works out well for us because we also want u to be something that if we keep taking the derivative, eventually we get to 0, right? And so if I keep taking the derivative of x squared, I get 2x, and then 2, and then 0. So, eventually if we did have to keep going, it would get to 0 anyway. So that kind of tells me that I'm going to let u equal x squared, and then dv is going to equal e to the x dx. Okay, so now I know that the derivative of u is 2x dx, and v is very simple. It's the antiderivative of that. That's just going to be e to the x. All right, so let's go ahead and plug into our parts formula over here. So we have uv, which is going to be x squared e to the x minus the integral of v du. So v is e to the x, du is 2x dx. Okay, and so now we again are looking at this integral right here, and we have to figure out, well, how do we integrate that? And it doesn't look like it's one that's easily done right away. However, it looks like one that can be easily done using anti-differentiation by parts. So we're going to go ahead and do that again. I'm just going to choose a different color here to kind of highlight that. So now with this part here, I'm going to let u, again, I want to kind of follow along the same path. So u is actually going to equal this 2x part, right? It's the part that's easily differentiated, and if I keep taking derivatives, eventually it goes to 0. So u is going to equal this 2x, and that means that du is equal to 2 dx. Okay, dv is still going to be e to the x dx. All right, the rest of that integral right there, and v would then still be e to the x. Okay, so now as we go ahead and we plug this part into our formula over here, we still have our x squared e to the x minus, and I'll go back to using the green color here, and then we have uv, so that would be 2x e to the x minus the integral of v du. That's going to be e to the x times 2 dx. Okay, and if we look at this part here now, okay, this is an integral. That's not so bad, right? I can take out the constant. I can put that out front. So let's just go ahead and rewrite it so we can see it. So we're going to get x squared e to the x minus 2x e to the x. I'm going to go ahead and distribute that negative. That's going to be plus 2 times the integral of e to the x dx. All right, and now I know what, the pen got caught right there for a second. Let me just fix that. So if I look at that integral right now, that 2 times the integral of e to the x dx, like I already know what that comes out to, right? The antiderivative of e to the x is just e to the x. So our final answer, right over here where we got a little bit more room, is going to be x squared e to the x minus 2x e to the x plus 2 e to the x, right, because that would be the antiderivative right there, plus c. Okay, so this whole thing here would be the antiderivative of our original integral. Okay, so you can see using anti-differentiation by parts can be a bit challenging. Sometimes you have to do it more than once, but really the trick comes in finding what to use, or what to set equal to u, what to set equal to dv, and then working from there. Okay, so sometimes if you pick the wrong item for u or the wrong item for dv, you may have to go back and start over. really the goal is that you want it to be able to get simpler as you work through it. So a couple of tricks I can give you is make sure that u is always something that is not only easily differentiable, but the other thing to look for is if you keep taking derivatives, the second derivative, third derivative, fourth derivative, will it eventually go to zero? Okay. For dv, you always want something that's easily anti-differentiated. In other words, you want to be very easy to find the antiderivative of whatever dv is. Okay, so in this case here we had e to the x. In the case before, we had cosine x, where the antiderivative was sine x. So those are some tricks you can use. But it's one of those things where it takes a little bit of patience and it takes some practice to get used to. All right, so good luck, and I will see you in the next video.